Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's great to have Ule here again, visiting from Chalmers University. Ule will be staying till the end of this month, and his talk is about counterexamples in the central limit theory of Markov chains.
Thank you. I'm very happy to be here again. I was here very briefly in 2000, and now it's a slightly longer stay. So I'll be talking about central limit theorems for Markov chains. When the Markov chain has finite state space, that proving central limit theorems is quite straightforward. So I very quickly go through that, and then I'll move on to infinite state spaces where the whole thing becomes more of an issue. So we take, everything will be in discrete time. So x naught, x1 dot 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 is an irreducible Markov chain, and we denote the state space by S, and we have an arbitrary function f, a real valued function f of the state space, and look at the long-term behavior of the sum of f along the sample path in the Markov chain. If we take the chain to be irreducible, then it has a unique stationary distribution. So let's write pi for this stationary distribution. And in this case, the asymptotics does satisfy both laws on large numbers and the central limit theorem. There are various ways to do it. I think I like to do things as probabilistically as possible. So I prefer the regeneration approach, where you single out a state S1, and you look at excursions that the Markov chain does from this until it returns to the same state. And these excursions are going to form IID blocks, and you can then apply laws of large numbers and central limit theorems to the sums after the block returns, and there's a little bit of filling in to do, but that's quite straightforward. So the law of large numbers says, of course, that the average of f along this sample path, as j goes from 1 to n, tends to the mean given by the stationary distribution almost surely. And the central limit theorem tells us that if we subtract the mean and divide by square root of n, then this thing tends in distribution to normal with mean 0 and some variance, which is given by the following expression. Here tau 1 is the expected time duration of an excursion from the state S1. And the sigma f squared is obtained by taking expected mean square deviation between the sum along an excursion minus, I guess everything is simplest if we just subtract mu f from f so you can forget about this part. But assuming mu f is 0, this is just the variance of what you get during the sum of the f's during one such excursion. And you have to divide that by the expected time, which is always finite in a finite state Markov chain.
It doesn't depend on S1?
It doesn't. So I don't know of a direct argument for showing that this quantity doesn't depend on S1. But since the central limit theorem holds with this sigma f for any S, it's clear that it cannot depend on it. Okay, so let's move on to infinite state spaces, and the state space could be countable, but it could also be uncountably infinite. So some, of course, central limit theorems won't hold in total generality, so we need some assumptions. And what I'm going to assume throughout is that the Markov chain has a unique stationary distribution, pi, and that the chain is ergodic in the sense of total variation convergence to the stationary distribution, no matter what we start from. So the total variation distance between two probability measures is given by this expression. You look at the supremum over all events A of mu of A, that's one of the probability measures, and nu of A, the other ones. So the maximum discrepancy between the probabilities when you range over all possible events. That's the total variation distance. And the ergodicity of a Markov chain is defined in terms of this. The chain with transition kernel P, unique stationary distribution pi, is said to be ergodic if the n-step transition kernel starting with any given x converges in total variation to the stationary distribution pi. So we can refine this ergodicity notion by putting constraints on how fast this thing goes to 0. So if it goes exponentially fast with a multiplicative constant, so there should be a rho less than 1 such that the total variation distance decreases like rho to the n, and that this multiplicative constant may depend on x. Then we call the chain geometrically ergodic. And if moreover we can take this constant to be independent of x, then we say that the chain is uniformly ergodic. And you could go for an alternative definition of uniform ergodicity, where you just want the total variation distance to go to 0 in a uniform way over all chains and not require this geometric decay. But in fact, that follows from that other candidate definition of uniform ergodicity. So uniform ergodicity, however you wish to define it, is going to be stronger than geometric ergodicity. Okay, in the infinite setting, f is no longer automatically bounded, so we need to worry about moment conditions. And of course, we also need to take f to be measurable. So a natural candidate for a moment condition for a central limit theorem is, of course, that the second moment under the stationary distribution should be finite. And there's a classical result of Cockburn from 1972 stating that uniform ergodicity and this moment condition, finite second moment under the stationary distribution, together imply a central limit theorem with this classical 1 over square root of n scaling. So that's well known. How about if we weaken the assumption of uniform ergodicity to just geometric ergodicity? Then there's another classical result, Ibragimov and Linnik, 1971, also proving a central limit theorem. But they need a slightly stronger moment condition. So a second moment isn't enough for their approach, but 2 plus epsilon moments. Given any epsilon bigger than 0, 2 plus epsilon moments will be enough for this central limit behavior of the Markov chain. So there's an obvious question here, namely whether we can remove this epsilon from the result, weaken the moment assumption a little bit. And if you're free to put extra assumptions on, the answer is of course yes, and we already saw that for uniform. Yeah?
Show the previous sheet
Yeah.
again, please, because I was kind of not paying very close attention. What does epsilon come in?
We're asking that the 2 plus epsilon moment should be finite. So rather than a 2 plus epsilon moment, would it be enough to have just a finite second moment? And we saw that if we strengthen the ergodicity to uniform ergodicity, then the answer is yes. And it turns out that for reversible Markov chains, the answer is also yes. Maybe formally this result is due to Roberts and Rosenthal, 1997, but there's a whole host of different central limit theorems under slightly different conditions. In particular, one of Kipnis and Vardan from 1986, which is very close to this result. So there's a big industry here, especially for reversible Markov chains. But okay. Roberts and Rosenthal, in a later paper from 2004 or something, a survey paper, they raise they highlight this problem then of whether a second moment would be enough for geometrically ergodic Markov chains. And I decided to look into that and realized by means of a counterexample that a second moment is not enough. So here's my result. There does exist a geometrically ergodic Markov chain with stationary distribution pi and a function f from the state space to the reals, such that f does have a finite second moment under the stationary distribution, while for no choice of sigma squared does these normalized sums converge in distribution to a normal with
an easy way to see why, if for instance, if the 10th moment is bounded and it's geometrically ergodic, why it should hold?
I cannot answer that off the top of my head. Presumably it's not terribly difficult, but no, if you would force me here to try and do it, I would go about this regeneration approach, but I'm not sure exactly where that would lead. But so it's a good question. I cannot answer it. But we're going to look at this negative result here, that the second moment, the finite second moment is not enough. So how do we cook up a counterexample? Well, the first thing to notice is that since the result does hold for reversible chains, we need to find a non-reversible counterexample. And the way I think about non-reversibility of Markov chains is the existence of circuits in the sample in the state space, which are easier to traverse in one way than the other. And the very simplest setup here is to introduce a single, a special state which we call 0, from which we do circuits like this. Once you enter one of these paths, one of these circuits, you're forced. So these are transition probabilities. There are 1 all the way. So the only randomness is where you go from state 0. And introducing this central state here is of course also to set things up for a regeneration study. So so we can toy around with Markov chains of this kind and see what happens. So more formally, we can take the state space to be this 0 state together with S tilde, which we take to be triples A, B, C, where A is positive, B is an integer less than or equal to A, positive, and C is plus or minus 1. So let me tell you what this means. A is the length of this circuit. B is the number of steps left on the circuit. So when we enter a circuit, we start with A equal to B, and then there's a countdown going on. And C is going to be a plus or minus 1, and that's we only introduce to regulate the function f, because things will be easier if we can make f have mean 0, and this we make f symmetric under the stationary distribution by having for each fixed length A we have 2 circuits of the exact same length, and one has C equals plus 1 and the other has C equals minus 1. So I've basically more or less described the transition mechanism. So if you're in a state A, B, C, if B equals 1, that means that this is the last step of the circuit, then we jump to 0. Otherwise, we jump to A, B minus 1, C. So just one step of the countdown. And then there's the issue of where 0 jumps. And we jump to 0. It jumps to itself with probability 1/2. And we have this, as I said, we only jump to other states A, B, C if A equals B. And this will be with probability 2 to the minus A plus 2. And you can check that this sums to 1 if I did it right. Okay, so one point of this is that when the chain is in stationarity, the set of regenerations, the times when we return to 0, is going to be like a Poisson process. When we're at a 0, we have probability 0, probability 1/2 of going to a 0 again, and these excursions have exponentially decaying length with parameter exactly 1/2. So the time you wait until the next 0 is geometric with parameter 1/2. So the zeros, if you're just interested in whether the chain is at 0 or not, this becomes an IID sequence with parameter 1/2 in the stationary distribution. So that means that we have very the thing mixes fast when we're not in some circuit, a huge distance in a very long circuit. As soon as we get back to 0, we're very near stationarity. So here's an expression for the stationary distribution. I guess instead of, since the chain is irreducible, I can change a stationary distribution to the stationary distribution. And the second thing I said was that these events, xn equals 0, are IID when the chain is stationary. And yes?
Show that again.
The second pi, should it be divided by b instead of 2 to the minus b? Or divided by a, sorry.
And shouldn't you divide this by a?
2 to the minus a over a.
Why is that?
Aren't all positions on the cycle equally likely?
Yes.
What's it, the 2 to the minus? A
So,
plus 3.
a plus 3. Yes, we had a plus 2 in the previous,
I thought it's b.
in the jump probabilities, right? When we jump from 0, we jump with probability 2 to the minus a plus 2. And in order at time 1 to be in this state, we have to be in state 0 before, and that has probability half. So I think these two slides are at least consistent with each other. Okay. Using this IID property of the returns to 0 together with the coupling argument, it's straightforward to show that the chain is geometrically ergodic. But it's not uniformly ergodic, because if you start the chain in the beginning of a very long excursion, it's going to take a long time to reach stationarity. So there's no uniformity in the choice of starting point. Okay, so now it remains to construct the function f, which will yield this counterexample. And if you want to show that something is not normal, one good way is to show that it's Poisson, or approximately Poisson, with a small parameter. So here's a way you could go about. We introduce two sequences, capital NK and delta K, such that NK goes to infinity very fast, delta K goes to 0 very fast. The delta K's are powers of 1/2. That's just in order that we can find states that have stationary probabilities to be exactly delta K. Yes, so we pick such sequences, and then we define a sequence of states chosen to have these probabilities delta K under the stationary distribution, and then we take fs1 equal to capital N1, a large number, fs2, N2, an even larger number, and so on, and then we take fs equal to 0 for all other S. Now, with a reasonably clever choice of these NKs and delta Ks, we can hope that for certain arbitrarily large n, the distribution of the square root normalized sum is dominated by a single state SK producing these large things. And I see here I'm not subtracting any mean here, so I guess we should actually duplicate these states. Each state has a mirror state in a circuit of the same length, right? So, and we can put that state to have f equals minus nk, so to get this to get rid of the non-zero mean. Okay. I'm sorry?
Type the delta k.
What?
What are those numbers? The delta k.
What are they? They're just very small.
No,
Very
what was their...
okay. So delta k is a large power over half, and I'm choosing the state sk such that sk has stationary probability delta k. So if delta is 2 to the minus 1000, I choose sk in an excursion of length 998 or whatever. Okay, so if this distribution is dominated by a single sk with delta k of the order 1 over n, so that we expect to see on the average one such non-negligible value of f, then the distribution will look more Poissonian than normal. N is the how long time we look at the Markov chain. Okay, if you work out this procedure and insist on getting this kind of behavior, then it turns out that this implies that pi of f squared, the second moment of f, becomes infinite. And we wanted an example with finite second moment. So this approach doesn't quite work, but we can modify it. And the modification is quite simple. Namely, we chose this state sk on an excursion like this with a large value f equals nk, and if we instead smear this f out, so on the whole excursion, so instead of having f equals 0 in each state except for one where it takes a very large value, we average out over the whole excursion, then you can get the second moment down to being finite while keeping this quasi-Poisson property of the example. And I'm not going to give you any further details, but the core of the calculation is that if we want to smear out this nk over small n different sites, then if we didn't smear out, we would get the contribution to the second moment would be nk squared. But when we smear out, we get this n squared in the denominator in n different terms. So we get a factor 1 over n here, which brings the second moment in the stationary distribution down compared to the more primitive approach. And that turns out to be enough to construct the counterexample.
But this can't work any further, so why can't you smear on and control the third moment and so on?
I don't think I have an easy answer to that either. Yeah, this is.
But in this particular example, it's clear, right? In your particular example, it's clear that you've smeared all you can.
Yes.
So what you're in a sense doing is creating dependencies between visiting states of high value because they sit on the same cycle, whereas before you did the smearing, they're almost like independent. You either visit it or some other things.
Yeah, you're right. There's as much smearing as possible in this for this particular structure of the chain. Okay, so I won't say any more about this. One more thing. After I published this, I was contacted by Richard Bradley, who pointed out that there was already an example from one of his papers from the 1980s, a Markov chain, which does have precisely these properties. Though the properties were not stated in his paper, but if you combine some remarks and results with a couple of other papers, you can quickly deduce that it serves as a counterexample to this hoped for generalization of the CLT. So I wasn't sure whether I should publish an acknowledgement of priority, but eventually I wanted to err in the right direction by doing so. And he was very, very kind about it and praised the pedagogical qualities of my example and so on. But and I got one more MathSciNet item by publishing this acknowledgement of priority. So.
Maybe you could have published it in two separate, two parts, one acknowledging and one explaining.
Yes. Okay. So I now move on to some more recent and in fact ongoing work with Jeff Rosenthal. So as I mentioned, it was this survey paper by Roberts and Rosenthal that inspired me to do this other work. And this summer, Jeff contacted me again concerning converses of central limit theorems in Markov chains. So what we're doing here is inspired by the result of Kipnis and Veridan that I mentioned before. So their central limit theorem says that if the Markov chain is stationary, ergodic, and reversible with a finite second moment in stationarity, and if the variance of the n-step sums normalized by 1 over n, if these tend to some finite sigma squared, then in fact the sums normalized in the same way converge to a normal distribution with variance sigma squared. So Jeff's question here is whether a converse holds. If we do have this convergence, do the variances, do the normalized variances converge to the same thing? So I state this question again here. Assuming the chain to be stationary, ergodic, and reversible with finite second moment, and if we have this asymptotic normality for some sigma squared less than infinity, should the 1 over n normalized variance, is it then necessarily the case that the 1 over n normalized variance tends to sigma squared? And we don't know the answer to this, but we did find a couple of counterexamples. The first one that we came across was that dropping reversibility means that you can have this normal convergence but have a totally different, in fact, infinite limiting variance. And the same thing can happen if we drop the second moment assumption. So I went through this quicker than I expected, because I hadn't prepared to describe these examples in detail, but I think I can still explain them without the help of the slides. So let's first consider the situation where we drop both reversibility and the second moment. Then it's in fact really easy to find a chain which has bad variance behavior and still satisfies a central limit theorem. And again, we can think of the chain as having this central state 0 and making excursions. These forced excursions are only possible if in the non-reversible situation, right? So this time the excursions will be really short, just to one state, to the next state, and then back. And we'll have cancellation on this circuit, so that the first step f takes some maybe large value n, and then in the second state it takes a value minus n, and then it goes back. So everything is going to just sort of cancel, except possibly in the beginning of your sample path. You might have started at the second step of such an excursion, and maybe also in the last step of your sample path. Now, so the only thing that contributes to the sum along the whole sample path is the first and the last step. And when you divide their contributions by n, they're going to disappear in the limit. So we're going to have this central limit behavior with the 1 over square root of n scaling, but in the slightly degenerate sense of having 0 variance. If you don't like that degeneracy, it's easy to add, let's say, IID pluses or minus 1s to the f. You create a product Markov chain, for instance, to do that, and we'll have convergence to a standard normal. While if we make the we're going to have an infinite number of possible excursions, and the value of f on the excursion, we can let that have as bad moment properties as we want, and in particular we can give it an infinite second moment. And then if you have an infinite second moment and you divide by n, it's still going to be infinite. So that's sort of a cheap counterexample. Yes?
Just a quick question. If the second moment is finite, does it imply that there's a subsequence for which so if the second moment is finite and you have the first statement, does it imply for a subsequence the second statement?
This one?
Yes.
I don't think we know any more about that question than the full question. Because the counterexamples that we do have, they behave so badly that you can't have convergence on the subsequence. Yeah. But it might very well turn out in the end that what you're asking about could be the case, that we have convergence along the subsequence but not the full sequence. It's a good question. Okay, so we can modify this example I just explained to recover this second moment condition. And we can in fact make f bounded if we, in an appropriate fashion, replace, if we have this excursion where you jump to f equals n, f equals minus n and back, we can instead make it a longer excursion where f equals 1 for n steps and f equals minus 1 for n steps and come back. And you just have to make sure that the expected excursion length has finite first moment, otherwise the stationary distribution will disappear on you, and that'll work. So that's the counterexample where reversibility is dropped. If we insist on reversibility, we still have a counterexample, but then we have to drop the moment condition. And I thought for a long time, when thinking about this problem, that there wouldn't be such a counterexample. That in the reversible case, you couldn't find anything even if you dropped this. But and the argument would be a kind of regeneration analysis as before. But it turns out that, again, in the non-reversible case, we are relying heavily on the cancellation in excursions, and that's hard to achieve in the reversible situation, because the chain can, if you have a circuit in a reversible chain, then the chain can walk back and forth in this, and there's not going to really be, it's hard to control the cancellations. But if you do the following, if you have an excursion again of length 2 in such a way that you jump to one of the states, and then you jump back and forth between these two states for a long time, it's going to be approximately an exponential amount of time. And you have these two states you take f equals n in one of the states and minus n in the other. So there's going to be a lot of cancellation when the chain jumps back and forth. And if you cook up the excursion lengths in such a way that the expected duration of a circuit has finite mean that you need in order to, otherwise the stationary distribution disappears. But the size biased, the length biased a length of an excursion becomes unbounded or infinite, then in such a situation, this is well known from renewal theory. You can have renewal sequences that, if you with finite renewal epochs, but if you start stationarily, the time until the next epoch is going, until the next renewal is going to be infinite, and you can use that kind of trick to achieve this reversible counterexample. And I won't give any more details here, so I'll stop. Thank you for your attention. So Elchanan, I think you heard Jeff talk about this earlier this summer or something, right? So that was...
Questions? So what do you believe regarding having a counterexample that has both features? Do you believe in that, or you think that there's a theorem that these two imply autonomous?
Yeah, so I've been sort of going back and forth between one belief and the other, but at the moment, since I spent more time looking for the counterexample, or at least more recently spent more time looking for the counterexample than from proving the positive result, I'm leaning towards belief in the positive result. but who knows? And I mentioned to Jeff that I was going to speak to this audience, and he got all enthusiastic and thought that maybe somebody here in this wonderful group could solve the problem for us. So anything in that direction would be highly welcome.
Other questions? Thank you.